Okay, so let's get started. Today I will talk about TaylorDiff, which is implementation of higher order automatic differentiation and about its applications. So because we are in this symbolics and numerics track, I will specifically focus on how to use symbolics tricks to make this better. This is the outline. First, I will talk about what is Taylor mode AD and how we implement that, specifically how we use symbolics to automatically synthesis rules for higher order automatic differentiation. And then we will talk about several applications like solving nonlinear equations and ODEs, which many of the Julia community should be interested. And so first part, let me just give some background about higher order derivatives. So for a function that maps Rn to Rm, the full derivative of it has like m times n to the power of p elements. So it's often prohibitively expensive, but actually many applications don't actually require that full derivative. And so we focus on a specific type of higher order derivative, which is the higher order directional derivative. So if you are familiar with AD, you all know that what is a Jacobian vector product? It is just f prime x times v, and you can extend it as to second order, which is called Hessian vector product, and you can extend that generalize to multiple orders, and we will use the bundle notation f0 f1 towards fp to be the higher order derivatives immediately contracted with several vectors. So these are called directional derivatives. If you try to do this with nested forward diff, well, it's doable. But the mechanism that forward diff achieve that is it will create a dual number pair for each order of this differentiation. So when you nest it again and again, it will double the numbers of operations each time you increase one order. So it's like 1 times, 2 times, 4 times, 8 times. But actually, Taylor mode is another technique that try to do the same thing with much faster speed. The technique here is how we can build such an automatic differentiation system with higher order chain rules. Because if you learn about the first order AD theory, you will notice that the core principle here is the chain rule. So if fx equals to g of h of x, and you know the function value of h and its derivative, and you know the chain rule, you can always propagate over the function g and get what is fx and what is f prime of x. Okay, and in order to do that, you need to define a lot of building blocks, which is known as first order primitive, or also called first order derivative rules. When you have all these rules and building blocks, you can actually have a robust automatic differentiation package that handle a lot of different function definitions. And similarly here, for higher order AD to work, we just need a equivalent of chain rules in higher order contexts. Technically, it is known as Faddy-Bruno's formula, but I will avoid using this name. Just call it higher order chain rule. And as you expected, higher order chain rule is capable for propagating H0, H1 towards HP using our bundle notation to F0, S1, and Fp. And fortunately, for all the elementary functions as well as many special functions, we have some recursive computational tricks to evaluate the higher order chain rule very quickly. It is guaranteed to be at most O(n) squared and in many cases linear, which is a lot better than the exponential case when we see in nested for first order differentiation. Okay, and then just a very little demo on very simple functions, but you can see that for these simple cases, you do see nesting the first order derivative is quite slower than just do this all at once with Taylor mode. And then let's talk about some implementation details. There are two different ways of viewing the differentiation problem. When you represent the bundle F0 to Fp, you can have a single array that first put all the elements. So imagine you have an array of elements. You can store the various order of derivative of the first element, all at one block, and then for the second element, and then for the nth element. But you can also have a separate array for each order. We will call these two things scalar mode and array mode. The benefit of doing scalar mode is that you always have a contiguous memory chunk for the whole array, because the order p is a compile time constant for your function, and actually the forward diff is always working in this way. But this have some disadvantages, because in order to do some linear algebra on such arrays, you cannot just call into BLAST or LabPACK. You need to use the generic linear algebra routines defined in Julia base, which is not always optimized. So it should be good for nonlinear operation dominated function body, but may not be as good for linear operation dominated. And we get some inspirations from a package called forward-diff2, which is developed by Ma Yingbo, which is a previous Julia Hub employee. And so we will introduce the array mode in TaylorDiff, and so that we can do both scalar and array mode for this higher order differentiation. And for both scalar and array modes, as I've mentioned before, the order p is a part of Julia type. So that using the Julia multiple dispatch mechanism, we can always specialize on the type parameter, and we can always stack allocate all the values and derivative partials, especially beneficial for the scalar mode, where then you will have a whole contiguous chunk of memory for this bundle. And this will also allow some more aggressive optimization, such as unrolling the loops in the primitives. And this is what previous AD packages like TaylorSeries.jl in Julia, which roughly do the same Taylor mode algorithm, but not as efficient as this implementation. Okay, so there's a quick demo of what I said before. When you construct a Taylor scalar, which is capable for propagating derivative up to like 2 order, and then you evaluate it on the exponential function, and it just boils down to very simple scalar operations, which should be efficient in Julia. And it doesn't need to allocate memory or have some very special instructions. No, just simple math. And we can demonstrate how powerful this specialization is with TaylorSeries.jl. If we go to here expansion of a considerable order like 20, you can see that in each of the examples, it is quite a bit faster than TaylorSeries.jl, which don't have specialization on the order parameter. And what's more importantly, we just said that how we can handwritten some rule for maybe the exponential function and maybe a couple of more, but we definitely don't want to write all the higher order rules, or we call them primitives, to support our differentiation, because we already have a library of rules which is called chainrules.jl, and chain rules is used by many AD packages like Zygote use that, Diffractor use that. I'm not sure if enzyme use that as well, but okay, enzyme maybe not using that. But anyway, if we can find a way to automatically make use of these rules in higher order context, then it will be very easy for library order to maintain the rules. So the trick is like this. We start with the recursive definition, which is g of h of x to the derivative of nth is like g prime hx times h prime of the n minus 1th order derivative. And then you can expand this with like the multiplication rule of high order derivatives. And in the end, this recursive definition will lower the expression by 1 order. And so you can always recursively evaluate that, although this is not very efficient. However, we can always unroll this recursive definition at compile time with Julia metaprogramming. And if you define all the primitives like this using symbolics is just like a mini compiler in the Julia language. You can always transform this kind of rules at compile time, so that in the runtime, the functions are already compiled and simplified, maybe doing some common subtraction elimination, and then you will get very efficient higher order primitives, although it comes from the more involved recursive definition. So in short, okay, the formatting is a little bit clunky, but if we have first order 80 rules in chainrules.jl and we have symbolics, then we can synthesize higher order 80 rules in TaylorDiff.jl. Okay, and then we will show some applications of this package. The first is nonlinear equations, which many should be familiar with. The first order solver is just using Newton's method. You compute the Jacobian and solve a linear equation and apply it to the vector x to update it. And we have the second order generalization of this Newton solver to be called the Halley's method. And it's a little bit more involved, but what's noticeable here is you have the term f prime prime x dot a, where a is another vector. Okay, so if you don't use higher order Taylor mode derivative, then f prime prime x may be not very computationally tractable, but it's very efficient in TaylorDiff.jl. So you just need to do this with no more than 2 times of the evaluation time of the original function f, and then you can construct this Halley's method. And because of higher order solvers requires fewer iterations, even in large scale problems, so as we demonstrate that with the discretized Chandra-Sekhar's integral equation, you can see that the speed up of using higher order method is actually bigger when the problem size is larger. And this is generally not true if you compute the full derivative, because the full derivative doesn't scale well with the problem size. Okay, and it can also be applied in the context of ODEs. For example, we have a ODE defined as u dot is f of u and t. There is a method called Taylor integration, which is just try to expand it, like u is a Taylor series and f is a Taylor series, and you plug into the ODE and try to determine, okay, for each order of t, the coefficient at left-hand side should be equal to the coefficient of right-hand side. But if you try to do this, you will instantly hit some problem, which is the definition of this ODE is actually recursive, because f is a function of u. So when you relate the various order of coefficients of the left-hand side and right-hand side, you will get something like u m plus 1 is the nth order coefficient of f, but f actually depends on u, which means that you at least need to know u0, u1 up to un to calculate this fn. So this is really not something that you can handle it with just one call to automatic differentiation library. The naive algorithm is like that. You first have u0, and then you compute f0, and then u1 and f1 and blah, blah, blah. But each time you get f, you need to invoke a call to automatic differentiation library. So it is like O(n) squared complexity. This is definitely worse than the state-of-art ODE algorithms. For example, we have some Runge-Kutta method, which is not as expensive as this. So if we just do it naively, then the Taylor integration method will not be better than other well-established ODE methods. However, we can do some simplification. And it's worth noticing that there is a previous package called TaylorIntegration.jl, which is based on TaylorSeries.jl, and it defines a very specific macro called TaylorWise. So if you have an ODE function, you can actually manipulate on that and try to handle this recursive definition explicitly and reduce all the redundant computations, redundant allocations to synthesize a more efficient function body to compute the all the coefficients un, so that you got a local solution near time t. Okay, this definitely works, but it's hard to implement because it is full of macro tricks, metaprogramming, and a lot of restrictions. And if you read the documentation of them, they will notice that this doesn't work in all cases, and it also doesn't make use of existing Julia infrastructure like symbolics, because symbolics, if you imagine that it's just a mini compiler inside the Julia language, so it is already very powerful, and it should be capable of handling this very simple case. So symbolics here can help to track the full computational graph on f. So with symbolics, we can have the full representation of computation happening in the ODE function f, and then directly transform it to a function to output the f0 towards fp, and then you can get u0 to up for an order p integrator. Okay, so well, this is a little bit out of the canvas. But anyway, this is just work precision diagram where you solve the same equation with different. Okay, maybe let's do it more. Okay, you can, so that you can see the whole plot. So we compare it with some state-of-the-art Runge-Kutta methods like TSIT5, Vern 6, Vern 8. And you can see that it is outperforming the method by the state-of-the-art method by quite a bit. And this is generally not true if you just use the naive implementation of Taylor integration. So it's symbolics that makes the Taylor integration method better. And of course, this is not very, this is just an initial attempt to develop these integrators. And the next steps, we might need to find some implicit method for stiff system. It could also beneficial. And also we can do adaptive order integrator for complex dynamics. So if you imagine that if you implement adaptive order for Runge-Kutta method, it's not very straightforward because each order of Runge-Kutta is very different. You need to do the tableau again and again. But for Taylor mode, each order implementation is very similar. You just need to vary the order parameter p and all the different integrator will just be compiled very seamlessly. Okay, so this is all for my talk, and I have to express my thanks to my collaborators, Bowen, Keming, Jiacheng in the Julia Lab, and also thank you, Professor Alan and Dr. Chris. Thank you. Welcome any questions.
Any questions?
Sure. Oh, where is? Okay.
Awesome. Thanks for the talk. I didn't catch the first part, but I'm just curious, have you tested this code or had reason to test it with outside of just like real numbers, say with like complex valued functions or things along those lines? Because that's something that I'm interested in with code is like generalizing ODE solutions to hyper complex number systems.
Okay, this is actually a great question. Right now, the TaylorDiff package only it will work with complex numbers, but only the analytical functions where you don't have something like z bar. So in this case, you can just treat the complex numbers as real numbers. And so if you want to handle this more generally, we might need separate treatment for like the real part and the imaginary part, which is not currently there, but we can definitely try to find some way to maybe utilize the rules defined in chain rules to achieve this for non-holomorphic functions.
Awesome. Thank you.
I'll admit I'm probably not a expert or anyone that truly understands what you're showing here that much, but do you have some real world applications that you can cite that you're specifically using this for, whether it's some form of chemical analysis, trial analysis, inclusion or exclusion on sets or something like that?
So there is a more complicated example in the paper related to this work, where we apply this to the Bruce-Slater's problem, which is a chemical reaction diffusion equations, which is contains high frequency and linear diffusion part and nonlinear reaction part, and the ODE solvers to solve this equation is like implicit solver because it is very stiff. And in order to do this, there is some nonlinear solving within this stiff solver, and TaylorDiff-based Halley's method can actually accelerate the nonlinear solve part of that specific problem. In that, I'm not sure if this level of application is what you are interested, but you can definitely check out this paper.
Yeah, that answers it. Yeah, that's what I was looking for. Thank you.
Also, like from the ODE side specifically, these are getting integrated into the ordinary FAQ, and as we if these continue to work well, we might start using them as default methods. We're a long way from that. These are still in implementation stages. But eventually this might be what happens when you call solve in an ODE in some cases.
More questions? Okay, thank you.
Okay.